Yeah, just did. Can you see the screen?
Yes, I can see the screen. Great. Microphone's yours.
Yeah, excellent. Yeah, I could probably begin, right? Again, thank you so much for inviting me and enjoyed the presentations. It was very fascinating to see the diversity of work that happens in this world where you're connecting the digital to the physical. I come from the area of manufacturing, and today I would like to touch upon some of the things that I know with my little vantage points as to what's happening in manufacturing when it comes to digital twins. And before I get into talking about the details, I would like to present Texas A&M's manufacturing group, as well as one of the centers under the Texas A&M manufacturing that I happen to coordinate, and then get into the details of how the smart manufacturing is increasingly beginning to use digital twins, and then provide a couple of case studies as time permits. First, about manufacturing, Texas A&M has one of the largest manufacturing groups, and those of us interested in looking at collaborations, the manufacturing group, as well as the work of manufacturing group, offers very fertile ground. I think it's a fascinating area from both digitization as well as creating digital twins of many of the things. And among the faculty, one of the key areas happens to be smart manufacturing, which to which my research kind of mostly belongs to. In addition to that, additive manufacturing, precision manufacturing, as well as nanobiocomposites become part of this larger spectra of manufacturing at Texas A&M. Also, in addition to people, we also have some world-class facilities, labs, as well as built equipment, as well as programs that might be of interest, especially if somebody is trying to virtualize as well as create digital twins of those. And we have excellent national as well as international initiatives, and also growing portfolio of education programs. And I would be glad to put you in touch with any of my colleagues based on your specific interest in the areas that I had just laid out. And coming to one of the areas, which is smart manufacturing, that I happen to work in, that area is really advancing and including digital twins as part of its advancement. Before I get into the details, let me give my view of how I see smart manufacturing. When think about manufacturing, people think about making things. And in recent years, the idea of making and maker revolution has taken off, especially with the use of 3D printing, as well as some advanced manufacturing technologies. In addition to the manufacturing platforms like additive, we are also seeing advances in the materials, AI, data science, sensors, wireless communications, computing systems like cloud and so on, and clean energy sources. The smart manufacturing is basically a platform where you can bring these together to advance the industrial footprint, especially as well as its impact on the society. And about the impact, if you look at manufacturing, it contributes 12% of the US GDP, and it's actually on the upswing given the times that we currently live in. And more importantly, from a smart manufacturing standpoint, there is a huge data opportunity that is yet to be tapped well. And that's where those of us who are into digital twins can find it to be a very fertile area. In fact, manufacturing generates more data than any other sector in the industry, including the government. However, very little of the data is used for many of the practical applications. And not just the academics, even the industry is fully recognized and seized of this issue. And then they're trying to go big way into the smart manufacturing revolution. So in other words, how can we use this data to understand the process and build models? Essentially, digital twins could be one way of building it or thinking about it, and use those models for effectively understanding the performance, as well as maybe monitoring and controlling the process. And at Texas A&M, my current research portfolio consists of things that are somehow anchored around smart manufacturing, both at the machine tool level as well as at the performance levels. And we have sponsors from both the industry as well as the government in advancing this work. And we are always looking for good collaboration opportunities. And when I say we, it's just not me, but 40 of us in the manufacturing group. Now I'm going to shift gears and then talk about how I see digital twins coming in and then advancing smart manufacturing. When we think about digital twins, one of the first thing that comes to our mind is digital twin for a particular mission. The photographs that I had shown you, right? So essentially, can we control the laser so that you can make sure you study its performance? And that's essentially what usually is thought of when people think about digital twins. But as we have seen from the diverse presentations today, there are lots of very interesting challenges at the systems level. I'm going to provide a quick case study to illustrate that, where the digital twin technology can really help us both monitor as in predict, as well as possibly control the performance of your system, the integrity of system, as well as help with maintenance of the entire plant. At the machine tool level, I'm not getting into the details because other groups pretty much look at some of the mechanistic aspects of how the various electromechanical components that are pertinent to a manufacturing shop floor behave, and how we can monitor their degradation, and then how we can actually ensure reliability of the various assets that are in your plants. But going from the systems to machine tool, there is something else that one needs to think about when we think about digital twins, which is at the process level. That is, once you have a big system on the factory has machines. The machines are executing some jobs, and that job needs to be really closely monitored, because that's where the quality of the product that you get is usually assured. While the systems level digital twins can help with assuring performance and integrity, it is a process level digital twins that we need to build to assure quality. And the remainder of this talk, I'm going to go into some specific case studies to illustrate some of the points that I just laid out, both at the system level and then at the process level. However, I will ignore the machine tool level discussion for a simple fact that it's not just germane to manufacturing alone, but various engineering domains actually have a similar kinds of challenges for digital twins, be it aerospace, any kind of transportation, building, as well as machine tools. Whatever operates its digital twin is basically similar to what I am thinking in terms of machine tool level digital twins. Okay. But the systems and process level actually are kind of unique to manufacturing. And that's why I will spend a little longer time on each one of those. First, let me talk about the systems level digital twins. And before I do that, I wish to say that much of what I'm going to talk about from this point are from two of my papers. On the systems level, I'm going to discuss based on the fourth paper. And at the process level, I'm going to talk about what's available in the first paper that I just mentioned. At the systems level, let's think about an automotive manufacturing plant. Suppose if you go to a factory floor where a car gets made. This is a typical video that you could actually can see how this process actually happens. A lot of people and a lot of stations and a lot of things that are moving, both the things that are getting made as well as the things that are helping with moving them as they are getting made. And also there are things that are tools that are helping transform them from the initial stage to the final stage. So in a typical manufacturing shop floor, you're pretty much looking at basically hundreds of thousands of dimensions of a state space to be able to monitor and then control. In other words, if you want to really understand a manufacturing shop floor, you have to think about maybe hundreds of thousands of variables and track how they are growing over time as well as in space. And that's what it takes to really mimic or basically create a true digital twin of a manufacturing plant. But that's just from a first principle standpoint. But there is something else that you can think about. Can we actually look at the actual data that emerges from these plants and then use that for building those digital twins? That is what I talk about here. And this data is becoming extremely prevalent and extremely abundant in these manufacturing plants. These plant floor systems that I talk about, that I see on the slide, every year they're growing at 6.5%, and then it's kind of garnering large market in the industrial shop floor. What they do is they go and then record the status of everything that's happening, everything that moves from place A to place B. And there is also something else, the software systems that talk about the higher level control when you're releasing a particular part to go from one place to the other, and when you're allowing a particular robot to go and then pick up a plot, and all those things are also controlled in a software level using what is called a manufacturing execution system. They are growing really fast. And more importantly, those of us who are aware of this Internet of Things sensors, they are really getting absorbed into the manufacturing environments. They are growing at 40% annually. So they're all together creating huge data load into the industry. And that is a huge opportunity, because if we can really use this data, maybe one of these days we can really create a good digital twin with which you can predict what's happening. So the researchers actually talked about the fact that you can use this data to effectively predict faults and breakdowns in a shop floor, and thereby bring 50 to 20% reductions in the cost that you expend for maintaining as well as holding the backup parts called the inventory and so on. And more importantly, if you don't do that with all the digitization that's happening in the manufacturing, you're going to see a similar kind of a catastrophic event, such as a blackout that might destroy the entire manufacturing network, because everything is now connected in the industrial environment. Now, let me spend the next 5 minutes talking about a few quick case studies here. A manufacturing plant, this is, I will not get into the details of where and what this plant is all about, but let's assume that this is a segment of your automotive industry where you are trying to make a simple component, which consists of a bearing as well as the race that goes into one of the engines or engine related parts. Okay. That particular small segment of the plant has about 20 machines, and they are connected together. The pod actually goes from this end to this end. There is another pod that goes from this end to this end, and then together they are all assembled, and then sometimes they are reworked and so on. So you will have multiple machines, multiple handling systems. They go through a very complex part, so complex routing and so on. But there is a lot of uncertainty. How long that particular part spends in each machine, it's not deterministic. When a particular part arrives, that's not very well known, because that depends on the demand and the releases and so on, right? And also the routes can change depending on what happens in the previous stage and so on. So essentially it's a complicated system. In order to track that, you really need to build a very effective understanding of the process and use the data. And here we are developing a manufacturing process-driven machine learning approach to address this challenge. And the challenge here is, can we actually predict the breakdowns of machines by using the data from some of these machine tools, the plant floor information systems? And we take advantage of our understanding of the manufacturing process, in the sense that we know that a part that is released from a particular location has only a finite places to go. And it has a particular recipe that it's executing. That is, a car has to actually go from wheels, and the wheels have to be under a particular bonnet and so on, right? So that's the whole kind of a idea that we build in to create a network, and based on that, we make the predictions. To get into some details of the matter here, what you have in the logs from these manufacturing environments are sheets like this. What they show is at different times, how long a machine has been working, and then what kind of fault it had, and so on, right? So essentially, every time the machine breaks down, it basically make a log of everything that happens to the machine. And it happens to every machine. So if you kind of convert this into some kind of a pictorial form, this is pretty much how it looks like. For every machine, you have times over which the machine was up, as in nothing was happening, 0. The machine was down, as in 1. There was some kind of a breakdown. And it also tells us how long the machine has been broken down. And if I just look at one portion here and zoom in on one area, just look at machine 1. Machine 1 has been up for a long time, but it was down for a short while. And before that, it was up, and then it was down for a little longer time. And same for machine 2 and machine 3 and so on, right? And the whole idea is, can I use this historic information to be able to predict the probability of the machine breaking down at every point in time in the future? And the probabilistic description of this is given by this hazard function H. So given all the inputs that you can gather based on this data set that we get about every machine, about how long this machine has been up, and for every machines, and then how long the machine was under repair for every machine, and also whether the machine is currently available or not. That is times that the machine has been up, the duration for the repairs, as well as the current availability of these machines. We can actually use this as an input to be able to make this prediction. How do we do that? That's basically takes us to this approach that we have taken. We essentially take this simple data from this machine to create this graph that I just mentioned, where you combine this data about when the machines were up, the repairs, and so on, and how they are connected. And then we actually build a machine learning model to be able to make that prediction. And in the interest of time, I'll skip all the details about the machine learning model that we had to build, as well as how we had to tune it because of some of the nuances of the manufacturing environment. Skipping all the details, I will talk about what this whole approach has led us to. So for this 20 machine project that we were doing with an automotive company, we were able to demonstrate for them that using our approach, we could reduce the error for predicting the faults by a significant amount. It's actually 2 orders of magnitude reduction. And more importantly, we could predict the impending breakdown of a machine using this digital twin that we built to an accuracy of about 90, errors of less than 10% within one shift. So in an implication for that manufacturing shop floor is that they could come at the beginning of a shift and look at the historic data, feed it into our machine learning system and the digital twin, and they can kind of get a prediction of which machines are likely to break down based on the historic information. And they can do that at the beginning of every shift, and then they can do it adaptively. And they can also go back and then trace back what may be the reason that may have been causing a particular machine to break down. So you can actually go and then create some provenance in terms of these things using this approach. And we are also working with using some additional data, IoT infused data, to make these predictions much more reliable, as well as do it over a much longer term. And that is the first case study. But I think we are kind of too close to the times that are allotted to me. But however, there is an interesting case study in the process level also, which I will not get into. But instead, I would like to conclude today's presentation by thanking the organizers for putting together such a fantastic event here on campus. And also the digital twin within manufacturing domain is an exciting area, both at the system level, the machine tool level, as well as the process level. But at the machine tool level, I hope my discussion gave us a glimpse to the idea of the complexity of a manufacturing environment, as well as how the use of some of these data-driven approaches with the good understanding of the underlying domain knowledge can help with coming up with addressing some of the innate problems like predicting breakdowns in a complex environment, localizing where it is, and also detecting what may be causing them. So with that note, I wish to conclude my presentation and thank you so much.
Thank you, Santosh. It's very, very interesting. So we have time for one quick question. Anyone from the audience? So Santosh, I have a question. Probably you have seen the demonstration at NVIDIA GTC. They demonstrated this whole factory of BMW, there's a digital twin of the whole factory there.
Yes.
And they have multiple production lines, and they simulate every single process of that. And so they have a pretty high fidelity. So now the question is, it goes back probably to the question that the team presented this morning about the fidelity of the digital twin here. So I understand that you are well doing this simulation, the study of the manufacturing process, mostly focusing on the process itself. But how do you think the fidelity of this of the digital twins that currently a lot of companies are looking into? Do you think that's something worth the effort, or it's something like overkilling at this point of time?
No, actually, that is needed. As I mentioned, depending on what our objective is, right? If our objective is to kind of understand how these machines as well as a system can break down and then address the reliability of it, the level of detail that I had presented and the data that is needed to build that kind of a model is sufficient. However, if you want to assure quality of the parts that are coming out of the manufacturing processes, you have to go look at the sensors placed into the machine, as well as combine that with the physical understanding of the process to really be able to assure quality. In other words, depending on the objective, you need to get into the right resolution of your digital twin. And the fidelities exist in bits and pieces. That much I can tell from my understanding of where the state of the art is. And from the process level understanding, you have to do a lot more. And one of the first papers on digital twin for additive manufacturing was produced by my former student who is currently moving to Virginia Tech. And when we look at what their group has done, as well as there is another parallel effort that's happening within Texas A&M on the similar kind of an issue, we are so far from really understanding as well as capturing and simulating the process, especially the nuances that determine the quality. So there is a lot that needs to be done. And then that's the huge opportunity that I would like to present this audience with.
Okay. Eduardo, I'm sorry. So we are a bit over time, and you can talk with Santosh.
That's okay. That's okay.
Yeah.
Hi,
Sorry.
Satish.
So Huayong, do you want to share your screen?